Hello and welcome to Chapter 2, Section 5, Zeros of Polynomial Functions. The objectives are to use the rational zero theorem to find possible rational zeros, find zeros of a polynomial function, solve polynomial equations, use the linear factorization theorem to find polynomials with given zeros, and use Descartes' rule of signs. The rational zero theorem. If we have a polynomial function and it has integer coefficients and p divided by q, where p divided by q is reduced to lowest terms, is a rational zero of f, then p is a factor of the constant term a sub 0, so that's the last term there, and q is a factor of the leading coefficient. So how we use this and what we do to this. This is the rational zero theorem, also known as the rational root theorem, because zeros and roots, remember, are interchangeable. So list all the possible rational zeros of f of x equals 4x to the fifth plus 12x to the fourth minus x minus 3. So the constant term is the 3 here, negative 3, sorry, and the leading coefficient is 4. So that means that we need to find the factors of the constant term, which are negative 3. And all my factors of negative 3 are plus and minus 1 and plus and minus 3, because 3 times 1 is 3. So we're going to do negative 1 times 3 and 1 times negative 3. So those are my factors. And then I'm going to do the same thing for the 4. So the factors of the leading coefficient 4 are going to be 1, 2, and 4. So plus and minus 1, plus and minus 2, and plus and minus 4. Now I need to write them as a fraction, and that's the factors of negative 3 over 4. So that's plus or minus 1, plus or minus 3 over plus or minus 1, plus or minus 2, plus or minus 4. So when we reduce everything, our possible rational zeros are plus and minus 1 and plus and minus 3, because I can divide 1 by 1 and I can divide 3 by 1. And then I would have plus or minus 1/2 and plus and minus 1/4, plus and minus 3/2 and plus and minus 3/4. So hopefully you could see what I was tracing. So those are all the possible roots of that function. That doesn't mean they're all necessarily roots. They're possible roots. So if I have to find all the zeros of f of x equals x cubed plus x squared minus 5x minus 2, what I'm going to have to do is list all my possible roots. Again, I'm going to look to the constant term here, which is negative 2, and the coefficient in front of x cubed, which is 1. So list all my possible rational roots. My possible rational zeros are going to be plus or minus 1, plus or minus 2, and for the constant term, negative 2, and then plus or minus 1 for the coefficient, which means, or the leading coefficient, sorry, which means my only possible roots are plus and minus 1 and plus and minus 2. So I have four possible roots here. So we're going to use synthetic division to see if we can find a rational zero among the 4 possible rational zeros. So again, our possible rational roots are 1, negative 1, 2, and negative 2. We will use synthetic division to test the possible rational zeros. So remember, it was 1, 1, negative 5, negative 2 for my coefficients. And I'm just going to pick one of the roots. It doesn't matter which one I pick. It doesn't matter which one I start with. We just try them and we keep testing it until we find a remainder of 0. So when I do my synthetic division, I'm going to drop my 1. And negative 2 times 1 is negative 2. 1 minus 2 is minus 1. Negative 2 times 1 is positive 2, so minus 5 plus 2 is negative 3. Negative 2 times negative 3 is positive 6, so negative 2 minus, or plus 6 is going to give us 4. Remember, that's my remainder. Therefore, that's not a root. So let's try -1. Same thing. Drop the 1 down. 1, drop the 1 down. -1 times 1 is -1. 1 and -1 is 0. -1 times 0 is 0. -5 and 0 is -5. -1 times -5 is +5. 2 minus -2 plus 5 is 3. And 3 is a remainder. So neither one of those work. Neither -2 nor -1 is a 0. So we continue testing possible rational zeros. So now we're going to try with 1 and 2. So if I do 1, again, I go through the process, I end up with -5, and that's not 0. So my last one is 2. This has to work. If it doesn't, then we did something wrong. And lo and behold, it works because my remainder is 0. So we have found a rational zero at x equals -2. That means that I can factor this to x minus 2, because if 2 is my 0, then that means x minus 2 is my factor. And then I have x squared plus 3x plus 1. Now we need to solve x squared plus 3x plus 1. And unfortunately, that's not factorable because there's no factors of 1 that add up to 3. So that is a quadratic formula problem. And when I solve the quadratic formula, I will have -3 plus radical 5 over 2 and -3 minus 5 over minus radical 5, over 2. And 2 is my last zero. I can write this in set builder notation, and I just include them in the brackets. Properties of roots of polynomial equations. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. If a plus bi is a root of a polynomial equation with real coefficients, b cannot be equal to 0, then the imaginary number a minus bi is also a root. Imaginary roots, if they exist, occur in conjugate pairs. So remember, wherever there's 1, there's 2. When you have complex roots, always have to come in pairs, or imaginary roots always have to come in a pair. And remember, real roots are where it crosses the x-axis. The total number of roots includes all roots. So solving a polynomial equation here, we have x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13 equals 0. First thing we have to do is list all of our possible rational roots, and we have 13 for our last term and 1 for our leading coefficient. So we're going to have plus and minus 1, plus and minus 13 over plus and minus 1. So my possible rational roots are 1, -1, 13, and -13. Again, we're just going to have to use synthetic division to check that out. And I have 1, -6, 22, -30, and 13 for my synthetic division. So here we go. Start with -1. When we do that, it does not work. Try +1. Typically, when I have to do this, I start with 1 and -1 because they're the easiest numbers to work with. And when we do 1, we see that we indeed have 0. So it is a root for the polynomial. So now we can rewrite this as x minus 1, and then x cubed minus 5x squared plus 17x minus 13. All right. So going back to that new equation we have, we're going to have to try our rational root theorem again, or list our possible rational roots. And again, we're back to 1, -1, 13, and -13. But because -1 did not work for the original polynomial, it's not necessary to test that value. So let's try 1. And look, 1 works here. And in this case, 1 is a repeated 0. So this means 1 has a multiplicity of 2, at least. So we can rewrite our original function as x minus 1 and x minus 1. And now I have x squared minus 4x plus 13. Again, there's no factors of 13 that add up to 4. Therefore, we're going to have to use our quadratic formula to solve. And when we do that, we get 4 plus or minus square root of -36 over 2, which means I have imaginary roots, so 4 plus or minus 6i over 2, that can all be reduced by 2. So it is 2 plus and minus 3i. So our solutions are going to be 1, 1, 2 plus and minus 3i. The fundamental theorem of algebra states that if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x is equal to 0 has at least one complex root. Then we have the linear factorization theorem. So it's basically just saying if n is greater than or equal to 1 and the last term is not equal to, or a sub n is not 0, that's the first term there, then we could have some function where we have a sub n times x minus c1 times x minus c2 all the way to x minus c sub n, where c1, c2, and cn are complex numbers, possibly real and not necessarily distinct. So in other words, an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors, where each linear factor has a leading coefficient of 1. So this time we're going to go backwards. We're given the roots and now or the zeros, and now you have to find the function. We have a third degree polynomial f of x with real coefficients that has a -3 and I as zeros, such that f of 1 equals 8. So that means when I substitute in 1 for x, my answer should be 8 once I get my function. That's going to come in useful. If I is a 0, then -I also has to be a 0, because again, that's complex conjugates. And we can go back to writing everything as linear factors. What I mean by that is we have x plus 3, x minus I, x plus I, and then we have some a sub n and f of x. Well, we can find a sub n in just a second here. That's what we're going to have to do. If we multiply x minus I times x plus I to get rid of the imaginary parts, we're going to have x squared plus 1. And then I want to multiply x plus 3 times x squared plus 1. You can use box method for that. I'm going to end up with x cubed plus 3x squared plus x plus 3. Okay, now we can then substitute in that f of 1 and 8. So it's going to be 8 if x is 1. And if I put in 1 for x and I set it equal to 8, I'm going to be able to find a sub 1, because this is the only thing I don't have. So let's solve that. So 1 plus 3 plus 1 plus 3 is 8. A sub n equals 8. So in this case, a sub n equals 1. Therefore, that polynomial function is just x cubed plus 3x squared plus x plus 3. All right, now we have Descartes' rule of signs. So we have some polynomial function with real coefficients. The number of positive real zeros of f is either the same as the number of sign changes of f of x or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f of x has exactly one positive real zero. Part 2 of Descartes' rule is the number of negative real zeros of f is either the same as the number of sign changes in f of negative x or less than the number of sign changes in f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. All right, so let's try this out. So for Descartes' rule of signs, determine the possible number of positive and negative real zeros. So this is my original function here. We have f of x equals x to the fourth minus 14x cubed plus 71x squared minus 154x plus 120. So to find the possibilities for positive real zeros, count the number of sign changes for the equation. So this starts out as positive, and then it changes to negative. So that's one sign change. Negative changes to positive, one sign change. Positive changes to negative, one sign change. Negative changes to positive, one sign change. So this has 1, 2, 3, 4 sign changes. So the number of positive real zeros of f of x is 4, 2, or 0. Because they have to change by a multiple of 2 and they're going to decrease. So 4, 2, or 0 positive real zeros. Then we have to try for negative zeros. So we have to put in negative x for x. And when we do that, we'll have x to the fourth plus 14x cubed plus 71x squared plus 154x plus 120. So as we look at this, there are no variations in sign change because they are all positive. So therefore, there are 0 or no negative roots for the function. It didn't ask me to find the roots, it just asked me how many possible positive and negative real roots there were. All right, we will practice this in class for sure.